Monitoring with Prometheus. So before starting, I would like to do a very quick inventory. How many of you have any experience with Prometheus? Like, ever you run it, local development, testing, production? Okay. Okay. And how many of you are running it in production? Just to understand, okay, I will set my talk speed and deep according to this. So, hello everyone. My name is Marco. I'm a software engineer. Recently moved to the DevOps side. I'm also a co-founder of Spreaker. I've been CTO there for several years. I recently, a couple of months ago, stepped back. I decided to focus full-time on engineering. And now I'm taking care of the infrastructure in our company. Spreaker is a podcasting platform. We do provide a service to create, host, distribute, and monetize audio podcasts. We are a small company. On the Spreaker product, we are 15 people, including 7 engineers, including 2 people on the infrastructure, and I'm one of those 2. Just to give you a little bit of context, we are currently hosting 40,000 active podcasts on the platform and reaching 50 million unique listeners on a monthly basis. I'm giving you this context because everything we do is basically a deal, is a trade-off between the ideal state and the desired state and the resources we have. Any technical decision we take must actually fit into a 2-people team and minds. And this actually explains a lot of the technical decisions we take on a daily basis. We try to keep our system as much as simple as possible without sacrificing reliability and scalability. So why do we care about monitoring? Well, we use monitoring mainly for 3 things. We need to know when things go wrong. When the things go wrong, we need to get insights in order to start debugging and investigating. And we use it a lot also to detect the changes on the system over the time in order to drive better technical and business decisions. We are currently deploying Spreaker on top of AWS. We are running it on 3 regions. Ireland and Virginia are the 2 core regions. And we are running some side applications on Oregon as well. And we are currently using Prometheus in 2 of those 2 regions, Ireland and Virginia, while we are still using our legacy monitoring system in Oregon. The idea is to run a Prometheus instance inside each region. So basically, we have an instance of Prometheus in Ireland, another one in Virginia. And the instance running in Ireland monitor all the targets, I mean the infrastructure applications in Europe, and the same for Virginia. The one in Virginia is monitoring all the stuff running in Virginia. So the idea is to keep the Prometheus server close to the monitored target. We monitor the infrastructure, first of all, in terms of EC2 instances. We call them nodes. Some stuff is running on top of Kubernetes, so we monitor the Kubernetes cluster health, VPN interconnection, blogging, backups, and so on. I mean, everything that's the foundation on top of which we run our applications. And we use Prometheus to monitor our applications, both running on containers or just on top of EC2 instances, and third-party applications we use as well. We also buy some services from external providers, so we use Prometheus to monitor external providers, and we recently started to monitor key business metrics as well. So why did we pick Prometheus? Well, first of all, as I told you before, for us it's very important to keep everything simple. Prometheus is actually a quite simple to set up and run monitoring system, but at the same time is quite powerful. It's backed by a time series database. I mean, I know many monitoring systems are backed by time series database. This is just one of them. And as a functional style query language called PromQL, that's pretty powerful and that we love. So what is this talk about? Well, obviously, it's about Prometheus from the user perspective. And especially, I tried to put myself into my day zero. I mean, I tried to think when we installed Prometheus, configured Prometheus, the service discovery, and then we set up a few exporters to begin. And then we started to use Prometheus for real to monitor our stuff in production. And so this talk covers some basic stuff I actually wanted to know before moving to Prometheus. You know, that actually I learned the hard way just with try and error continuously. So we are in a sort of change because we are running Prometheus version 1 right now, but 2 weeks ago, Prometheus version 2 stable has been released. Prometheus version 2 is basically a major version of Prometheus that features mainly a new storage engine completely rewritten from scratch. I mean the time series database, in order both to provide better performances on one side and fix some limitations that had Prometheus version 1. There are a few other notable changes, including the alerting, the way you configure an alert, the syntax that you use to configure an alert has changed between Prometheus version 1 and Prometheus version 2, from a DSL to YAML syntax in version 2. The examples I'm going to show you are the Prometheus version 1, but the same as the concepts in terms of architecture and design applies to Prometheus version 2, since I will not cover any deep topic like how the storage engine works or stuff like this, okay? The very first thing we learned about using Prometheus was not about Prometheus itself. It was actually about monitoring in general. So at the very beginning, we installed Prometheus and we configured the service discovery, few exporters, and we actually quickly realized that we were already ingesting a bunch of metrics. I mean, even deep data, like context switches or memory allocations of our applications, or the application garbage collecting statistics, okay? That's actually good, since the more data we have, the more insights we have about how our system behaves. But at the same time, when you start monitoring a new system, you should start answering basic questions, okay? Like, is my system up? Is it running? I don't care about garbage collectors if it's performant or not, okay? I want to know if my customers are getting a good service, first of all, okay? So we started answering basic questions in order to track key metrics, or the so-called golden signals. Is the system up and responsive? And if it is, how much more traffic can it support without disrupting the services? Or how much traffic can we support, or queries per second can we support while still honoring our service level objectives? There are a few methodologies that try to advocate golden signals. One is the 4 golden signals from Google. Another one is the use method. Among those, the one that we found most useful for our use case is the RED method by Tom Wilkie. That's super simple. RED stands for request rate, error rate, and duration. 3 metrics from which you can monitor the traffic reaching your system, the failure in terms of error percentage, and the performances, how much time it takes your application to generate the response. Now, even if this naming fits very well for, I don't know, HTTP-based applications, actually, with this method, you can basically monitor the majority of system. Think about a database, okay? The traffic can be the query per second your database is receiving. And the failure rate is the success or failed queries. And performance is the query execution time. Now, the RED method is actually closer to black box monitoring because what you're actually monitoring is your system from the client perspective, okay? What we usually do once we have monitored there's 3 metrics is reiterate on this and start tracking the saturation or capacity of our system. Monitoring saturation requires more knowledge about your system. Since, first of all, you have to better understand what is the bound of your system. Is your application CPU bound? Is it memory bound? Is it I/O bound? Is it a mix of them? So we usually follow this pattern. We start monitoring the red metrics. We start collecting other metrics as well. And then once we have more insights about how our system behaves on load, we add saturation monitoring, and then we reiterate on this. So once we have identified the golden signals, the next step is monitoring our golden signals. Now, before jumping into Prometheus, let me do a very quick recap of the Prometheus architecture in this slide. So Prometheus is mainly composed by two, let's say, main components, Prometheus server and the alert manager. There are a few other components like push gateway, but we will not cover it in this presentation. So the Prometheus server, well, first of all, Prometheus is a pool-based monitoring system. It means that the Prometheus server scrape the metrics from the monitored target, like your application or your node, your database, and so on. Using the HTTP protocol, so each monitored target should export the metrics in the, as an HTTP interface endpoint in the Prometheus format. Prometheus, first of all, features a service discovery. It supports several types of service discoveries, including Kubernetes resources on Kubernetes, not just specifically pods, but also services, ingresses, and so on. EC2 instances, DNS-based service discovery, other cloud providers like Azure, Google, and so on. Once discovered the targets, call the HTTP endpoint to scrape the metrics from the targets, store the metrics into the time series database, provide PromQL, that's a query language, to query those metrics, and allows you to configure alerting rules that are basically rules that are evaluated at the regular interval that fire or resolve alerts. For each alert that fires or resolve, the alert, the information about the alert is pushed to the alert manager, and the alert manager is responsible to dispatch the alert to the receiver, like the person that should receive that specific alert. Now, let's get back to our golden signals. So we want to monitor the request rate, the error rate, and the duration. So to monitor the request rate with Prometheus is actually quite simple. We can use the metric data type called counter. Counter is a monotonic data type. It means that its value must always goes up. I mean, you can only increment the value. Okay, you can never decrement the value. So let's say that you have an application. In this example, could be an application exposing an HTTP interface, like a web application. And let's say that we want to monitor the request rate of this application. In this example, we are defining a metric called HTTP request total, whose type is counter, that for each application instance export the total number of requests received from the application instance itself since its lifetime. I mean, since when the application started. So when you start the application, the counter will be 0 because you didn't receive any request yet. And then for each request, HTTP request you receive, you just do a +1 of this counter. This matrix is continuously fetched by Prometheus at a regular interval and stored as a time series. And so once you store this data as a time series, you can then query the time series, select a portion of the time series, like a time window, like the latest minute, and see how the data, how this value has changed over this portion, this time window of your time series, and then calculate some data, like the average number of requests received over this portion of the time series. We are used to, well, Prometheus allows you to attach labels to your metrics. Labels give you an extra dimension to your metric. They are free key value pairs that you can set and attach to your metrics. Everything is a string. In this example, or more specifically for HTTP-based applications, we usually split the metrics by method, the HTTP method of the request, the handler inside the application executing the request, and the response status code. These 3 labels give us enough granularity to actually calculate different metrics, as we are going to see. So once we export the HTTP request total metric from our application, we can calculate the request rate. So in the first example, what we are doing is we do select a time series. In this case, is HTTP request total. It's a time series selection. And then we specify a time interval. In this case, is 1 minute using the square brackets. And then the result of that selection is all the time series matching that query. So all the HTTP request total metric exploded for each unique set of labels that we exported from our application. The rate function allows us to calculate, given that time window, 1 minute, allow us to calculate the per second rate, increment rate of the time series. And if we sum all them together, what we get is the global request rate of our application. When you aggregate using like a sum function, you can also aggregate splitting by 1 or more labels. In this case, in the second example, we are summing by method. It means that what we calculate is the request rate by method. And we can do the same with method and handler or response status code and so on. Calculating the error rate is even more simple because we can reuse the same exact metric we already tracked. That's HTTP request total. Given an HTTP-based application, we can calculate the error rate as the total number of responses whose status code was 4xx or 5xx divided by the total number of requests received over that specific time window. So in this case, what we are picking is, in the first line, we pick all the time series matching the status code starting with 4 or 5. So we basically get all the status code starting with, so all the 4xx status codes and 5xx status codes. Keep in mind that Prometheus regular expressions are bounded, okay? So it means that it must start with number 4 or 5, divided by the total number of requests received over the specific time window, in this case, 1 minute. And what we get in output is a value between 0 and 1. That's our error rate. In this case, 0.02 is the 2% error rate. Pay attention that here we are using rate that actually calculate the average per second giving the time window, in this case 1 minute. But from a mathematical perspective, calculating the total number of errors in a minute divided by the total number of requests in a minute is equal to the total number of errors per second in a minute divided by the total number of requests per second in a minute. Okay, it's just syntactic theory. Yeah. Once again, we can sum by method and handler, and what we get is the error rate by method and handler. Average response time, it's not the best metric. I mean, response time distribution is a way better metric. It involves histograms, quantiles, and takes a dedicated talk just to talk about histograms and summaries in Prometheus. So I try to simplify a bit. Just talking about average response times, even if my suggestion when it comes to monitoring response time is to always use histograms that allow you to store the metrics into bucket and so calculate the distribution of response time given specific buckets you can configure. Now, let's get back to the average response time. So the average response time calculated using a time series can be seen as the sum of all the response times of all the requests received in a specific time window divided by the total number of requests that we received. For this, we need a new metric. And in this case, we are defining another counter called HTTP request duration seconds, where we sum up, splitting by the usual label, method, handler, and status, all the response times using the seconds unit. Keep in mind that all the values stored in Prometheus are float 64 bits. Okay? So even if you export an integer number, it's actually stored as a float and will be processed as a float. In this case, for each request we receive, matching the method get, the handler view user, whose response status code is 200, we sum up how many seconds, can be a fraction of seconds, obviously, it took to generate the response. And given this metric, what we can calculate is the average response time given a specific time window. In this case, we are checking the increase of the sum of the response times over the last 1 minute divided by the number of requests received over the last 1 minute. And what we get is the average response time, the global average response time of our application over the last 1 minute. As usual, we can sum by specific labels in order to get more details and to get more insights about our application. So, identify golden signals, monitor the golden signals. The next step is to alert on golden signals. Since the very basic question we wanted to answer at the beginning is we want to know when the things go wrong. So back to the Prometheus architecture, I was mentioning before the alert manager. So when you configure an alert, the alert is configured on the Prometheus server. The Prometheus server evaluate your alerts called alerting rules at a regular interval, like every 20 seconds, you can configure it. And when an alert fires or resolve, it pushes the information about the alert to the alert manager. So the alert manager gets the alerting input, it's a JSON, and allows you to configure a routing for this alert. That means, given this specific alert in input, who should receive the alert? Should be me, should be Jacopo, or who? It supports many channels to deliver the alert. We currently use email, Slack, and Opsgenie, but it supports many more. So the first metric we want to alert on is the high error rate. Now, the syntax you see in the bottom of the slide is the Prometheus v1 syntax. Okay, Prometheus v2 has the same concept, but the syntax is different, and they move it to a YAML. Okay, so in this example, we are alerting on an high error rate of our example application. So the cool thing about Prometheus is that any query you can run with the Prometheus query language to extract the data, like graphing the data on Grafana, can be used to alert on as well, just applying thresholds. In this case, we are using the same exact function to calculate the error rate, and then we want to be alerted when the error rate is greater than 0.01. That in the 0-1 range means when the error rate is greater than the 1%. There are a few things to care about and to focus on here. So first of all, we use a percentage threshold. Having an error rate threshold with absolute values doesn't make any sense. I want to get alerted if my application got 100 alerts in the last 1 minute. What 100 means? It depends on the traffic. So using percentage, what you are actually calculating is the ratio between how many succeeded and failed responses you generated. The second thing is the for clause. In this case, the alert will fire if the condition is true for at least 5 minutes. It allows you to avoid noise in alerting just due to temporary issues, like a an external services you are relying on is failing for 30 seconds, maybe you don't want to wake up during the night just because of this. Let's wait for a few minutes to see if the error continues. The third thing is the use of the without instead of by. So before, we were grouping our metric with by, method, and handler, or something like this. So first of all, the idea is to not alert on the global error rate. Let's say you have a web application, and a web application has several endpoints, like a website has the home page and then has internal pages. The home page receive an high load as an high traffic. Internal pages could have lower traffic. If you alert on the global error rate, the main problem you will face is that you will receive an alert only if the global error rate is greater than 1% in this case. The problem is, let's say you have an inner page that receives in total less than 1% of traffic, of your global traffic. But at the same time, this inner page fails 100% of the time. So even if the internal error page failing rate is 100%, if you alert on the error rate and your threshold is 1%, you will never receive the alert because the traffic hitting the inner page is actually lower than your global threshold. On the opposite, in this case, what we do is to keep the maximum granularity in our metrics and so in our alerting. So summing without a specific label means instruct Prometheus to keep all the remaining labels. So it means alert splitting by method and handler in our example. Okay, so we are explicitly asking Prometheus to keep the maximum granularity, just removing and grouping by the labels that doesn't make any sense in our specific case, like the response status code. Alerting on high response time is basically the same exact thing. The only difference is that here we don't want to alert using a percentage threshold. That probably doesn't make much sense. But we want to use absolute values. So throw an alert if the average response time of a specific endpoint of my application is greater than, like in this case, 500 milliseconds. Remember that the unit we used is seconds, so 0.5 is 500 milliseconds for at least 5 minutes. But the same concept we have seen for the high error rate applies to the high response time as well. So we have seen how to identify golden signals, monitor golden signals, alert our golden signals. The next step is to monitor something that doesn't directly export the metrics into the Prometheus format. So let's say that we use PostgreSQL, and PostgreSQL doesn't directly export the metrics into the Prometheus format. So what you use with Prometheus is the so-called custom exporter. Custom exporter is a tiny application that's specific for a specific target, like in this case, the custom exporter for PostgreSQL, that query the target you want to monitor using the protocol used by the target. So in this case, run SQL queries on PostgreSQL to extract the data and export the metrics using the Prometheus format to Prometheus server itself. Now, the question now I want to show you an edge case that at the beginning hit me a couple of times. So the question is, oh, sorry, yeah, before jumping to the edge case. So let's say that the custom exporters for Prometheus export a gauge called Prometheus app. For Postgres, export a gauge called Postgres app. It's quite common. It's like a value. In this case, it's a gauge, so it can go up and down. It's not a counter that's monotonic. Okay, that it's whose value is 1 if Prometheus is up and is 0 if Prometheus is down. And so what you tend to do is to create an alert when to get alerted when PostgreSQL is down on Postgres app equals 0. Okay, quite common. Now, the question is, well, what if the node running PostgreSQL and your custom exporter is unreachable, okay? And Prometheus can't scrape the metric from Prometheus. Sorry, Prometheus can't scrape the metrics from the custom exporter. Now, I'm giving you this specific example. We can talk an hour if it's better to run the custom exporter on the same node running PostgreSQL, or moving it on a different node, or running it on the same node running on Prometheus. But the same concept applies. What if Prometheus can't scrape the metric from the exporter itself? Well, the point is that the metric PostgreSQL hub will never reach the state 0, will never be 0. Because if the node goes down, PostgreSQL is down, but the latest data scraped by Prometheus was 1, and the next scraping will fail because the exporter is not reachable, okay? And so it means that our previous alert will never fire, basically. So how to fix it? Well, what you actually want is to get alerted when PostgreSQL app is 0, right? Like PostgreSQL is down and the custom exporter is up, or when the metric called PostgreSQL app is absent. You expect the metric to exist, but a metric has not been scraped anymore. That's the same exact condition to alert on. In this case, PostgreSQL is down. Maybe PostgreSQL is not down. It's just exported to be down. But you lose observability on PostgreSQL. And from my perspective, it has the same level of severity. If I can't trust anymore, my monitoring system is like the service I'm monitoring is basically down. We are a small team, but at the same time, we have internal teams as well. Not everyone does everything. We have people working on the front end, people working on the back end, the mobile application, the HUD technology, the monetization, and so on. And so our need is to route the alert by team and severity. When I mean team, I mean a group of people. It can be 1 person, 2 person, 3 person. So what you can do with Prometheus is attach labels to the alerts. Labels are like the metric label, free labels, key value pairs, strings that you can attach to your alert, and that you can use later on in the alert manager routing to route by labels. In this case, we are defining 2 labels, team and severity. In the spirit of keeping things simple, we just have 3 levels of severity, warning, error, and critical. So, and it changes when it's supposed to address the problem and the channel used to push the notification. So warning is something we can take care of the next business day. If a warning is raised on Friday night, we can wait until the next Monday to take care. And so we push the alert only on Slack, since that's the tool we use as an internal communication. We are a remote and distributed team. An error is something that should be addressed even during the weekend, but it's not so urgent to wake up during the night. So let's say it's something we should care of during the daylight, and we push it through email and Slack. Email and Slack. And critical, well, yeah, it's something we should address immediately, and phone call immediately during the night, and we wake up. This is an example of the alert manager configuration. The syntax I was explaining you before that changed between version 1 and version 2 is just the syntax of the alert, not the alert manager. So this work with Prometheus version 2 that actually doesn't make any sense because the Prometheus and the alert manager are 2 separate applications following 2 separate versioning. In this case, it shows how the routing by team and alert works. So routes are the routing is evaluated sequentially. And what you can do is any step of your routing can match 1 or more labels with exact matching using the match or regular expression using match underscore RE. And then you can have subroutes called child routes. So in this example, the alert arrives to the alert manager and enters the routing pipeline. And the first thing we do is the routing by team. So if the team name match front end, we enter the child roots. And then in the child roots, if the severity match critical, we route the alert through a receiver called page the front-end team by Opsgenie. And then you have to explicitly instruct the alert manager to continue. Otherwise, the alert manager stop the first matching route. And so the evaluation continues. And we match, again, the severity. If it's critical or error, page the team by email. And then always page the team by Slack. And at the end, just for the sake of clearness, but it's not required, continue false. That means stop evaluating the rules here and do not try to match again the next teams. At the end of this configuration, we have the fallback to the ops team. So all the alerts that don't have a specific team are routed basically to me and another guy. And in this case, we are not matching by team, but we are just matching by severity. And again, critical Opsgenie, error critical email, always through Slack. Each alert we define, at least in theory, should be an actionable alert. I mean, something for which it's not an informative alert. Okay, something has happened. You should take an action. You should do something. So for this reason, for each single alert we define playbooks, human readable playbooks that explain that briefly, in few lines, explain the problem, how to investigate, and in the past, how we solve the same problem. Keep in mind that we do alert only on things for which the resolution is not automatic. If the resolution is automatic, we don't alert at all. We just keep track of it in a sort of event log, but we don't use Prometheus for this. So in this case, we are using annotations. Annotations are pretty much the same of labels, but with a different scope. So are metadata that you can attach to your alert and that you can use later on to customize the message sent by the alert manager. In this case, we are linking the URL of the playbook, and when we receive an alert on Slack or by email or the same on Opsgenie, we always link the playbook so that even if you wake up in the middle of the night, you are very tired, you just click the link, you receive the alert, click the link, open the link, and in 10 lines, I get an idea about the problem, how we solved it in the past, and maybe a few comments I have to run if part of the resolution has been automated, but not fully automated. Just a little bit, a couple of words about the distinction between labels and annotations, because they are actually pretty much the same thing. It's metadata you attach to your alert. The very difference is the scope. So the labels are information used to identify the alert, mainly used by the alert manager for routing. Annotations are extra information, descriptive information about the alert itself. It can be a description of the alert, a textual description of the alert, can be the link of the playbook. Usually, even if it's not a strict rule, rules are read and consumed by a machine, by a software. Annotations are read and consumed by a human. So in this brief presentation, we have seen a few things. When we start monitoring a new system, first of all, we try to identify our golden signals, our key metrics. What are the most important questions we want to answer first? And then we do reiterate. Keep it simple. Start from the metrics that bring you value. Alert on those metrics and make sure that each alert is actionable. Okay? Otherwise, you're just throwing noise. Write playbooks for manual operations you have to do on the system, and, well, don't alert at all if actually the system is self-filling and the resolution is automatic. We are progressively migrating towards a self-filling infrastructure. We are doing quite good steps, and the number of alerts is reducing month by month. But there are still a lot of operations we have to do manually that are maybe scripted or partially scripted, but they have to be triggered manually, like a database failover. Right now, we don't have an automatic database failover. Database failover is fully automated, but it's triggered manually because we still don't rely, we still don't trust enough the whole monitoring system around our PostgreSQL database to ensure that it's not just a temporary network partition between the servers, the master and slaves, instead of the master is real down and so on. We are still working on this, and we will do. We have to do future work on this as well. I hope at least something I told makes sense for you. I hope you understood something. If you want to follow me on Twitter, I'm Pracucci. That's my surname. I tweet about this stuff. Keep in mind that Prometheus is not my daily job. It's just a little part of my work among all other stuff we have to do on a daily basis on the infrastructure and the evolution of our platform. If you have any question, I will be very happy to answer now or later. Okay.